I'd like to welcome everyone to this joint Dream Seminar and IUR Department Seminar. And it's my pleasure to introduce today's speaker, Jerry Ding. He was a Berkeley PhD student from EECS, graduated in 2012, I think, and has been working at UTRC, which is a really excellent research lab. Couple of locations, but he's in the Hartford, Connecticut location. So I'd like to thank Jerry for coming, and I'm really looking forward to your talk.
All right. Yeah, I think I have the mic. Right. Okay. Yeah. So just like Anil said, so I've spent 6 years of my graduate school career here, another year of postdoc. So it's been the first time being back in 5 years. So there are some things which are somewhat nostalgic. And of course, thanks for the invitation to come here and give this talk. So what I'll be talking about is essentially the Autonomy and Robotics initiative at United Technologies Research Center. Both a little bit of its history, how it got started within the autonomous helicopters domain, and then how it gradually migrated into this robotics domain, which is somewhat a more recent instantiation. So the thing to keep in mind is this covers a large body of work, essentially spanning the time between 2010 up to now. So it's a work a lot of different technical contributors. So in this talk, I'll just be covering a sampling of it in some of the areas I've personally contributed to. So this is an outline what I'll be talking about. So I'll start off with an overview of UTRC and UTC, what we are as a company, what we do, and how we operate. And then I'll go over a high-level overview of the Autonomy and Robotics Initiative, a little bit of its history and also its present focus areas. So in the next part, I'll just talk about a selection of different research topics that we're currently actively working on, and also in some of the areas I've specifically contributed to, so mostly in the planning domain. So here you have hierarchical motion planning, mission planning, and then collaborative autonomy, and also more recently, some of the human-robot interactions. Okay, so let's just jump in. So this is essentially an overview of what we are as a company. So UTC is a large, diverse global company spanning a lot of different business areas. So the 4 business units include UTC Aerospace Systems. So that's one of the major suppliers of aircraft components and subsystems. And you can find UTAS components on 80% of the aircraft that are in operation today. And then there's also Pratt & Whitney, which was one of the 3 major aircraft engine manufacturers. So actually, it manufactured one of the first high bypass commercial turbofans, which flew on the 747. And more recently, there's the geared turbofan, which is a new generation of these commercial jet engines, which just entered into service on Airbus A320 2 years ago. And then there's also the CCS business, which essentially is in the building HVAC and fire and security. So that includes Carrier, which is in the climate controls, and also the building HVAC business. And there's also Otis Elevators, which is in the business, of course, elevators, escalators. So this is a company with diverse range of business, a very long history. So what you see on here, a lot of founders of these companies, which are pioneers of their time, and they develop new technology and form entire industries. So just to give an example, so Frederick Rentschler is the founder of Pratt & Whitney. So he developed a lot of the early engines, which set up some of the first aviation records. So, the WASP engines were one of the first Pratt & Whitney engines. Is actually what Amelia Earhart used to fly across on her solo flight across the Atlantic. So, a lot of people like that, and the company continues to reinvent itself, of course. So, I already gave the geared turbofan example, but the oldest elevators. So for the amount of elevator, escalator installations around the world, it actually moves the world's population every 4 days. And also carrier air conditioning. So we actually supply the climate control system for the Sistine Chapel in Rome. So a lot of exciting projects are going on. So what is UTRC? UTRC is essentially the central research organization for the whole company. What we do is essentially both in part defining the new technologies, also maturing and transitioning these technologies into actual products, working with our business units. So essentially, well, we have the role of co-developing the technologies with our business units, solve some of the tough problems they face to make things a reality, and also serve as one of the hubs for interchange with external organizations, so with universities, with other industrial partners. So UTC has a long-term vision, and partly in part due to its long history. So we tend to invest in technology which may be still 10 to 20 years in the development. So we tend to carry a long-term vision in all the things that we do. And so this is just an overview how we're organized. So we have 4 different departments within UTRC. The one that I'm belonging to is the Autonomous Intelligent Systems. So that consists of control systems, intelligent robotics, system dynamics, and optimization in that kind of area. And then one of the new department that's forming is the Cyber Physical Systems department. So that consists of the cybersecurity, power electronics, formal methods, and embedded system, these groups. So myself is within the control systems group, so within AIS. So some of the other departments, so there's the physical sciences, so there's the advanced materials, environmental sciences, applied physics in that domain. And then there's all the thermal and fluid sciences. So this includes acoustics, aerodynamics, combustion. So some of the more traditional aero kind of topics. Again, we're a fairly global organization. So even UTRC itself, it has multiple locations around the globe. The headquarters is located in East Hartford, Connecticut. That's where I work at. So it's founded back in 1929 when we had Pratt & Whitney and also several of the aerospace companies came together to form the United Aircraft Company. So again, it has a very long history going back. But we also have locations elsewhere around the globe. So there's actually one right here in Berkeley, right down Telegraph Avenue, and there's also locations in Europe, so in Cork Island and also in Rome, Italy, and there's also an office in Shanghai. So there are a lot of places around the world. So what these locations lets us do is essentially tap into the collaborative working relationship with the local offices of the business units and also with the local university and industry partners. And of course, we're always looking for new talent to join us. So there are a lot of different opportunities we currently have available. So both full-time positions, internships. So a lot of different career tracks and locations around the world. So if you're interested, certainly come up to me afterwards. I'll be available. Yeah, we can talk. Okay, so with that, I'll just go into an overview of the Autonomy and Robotics Initiative at UTRC. So how it got started is essentially with the Sikorsky aircraft company. So there was an interest in developing optionally piloted vehicles, in particular for commercial or military helicopters. There's an interest in reducing the number of pilots who are sitting in the cockpit. So today there are 2 pilots. So there's a concept where you would have just one pilot sitting in the cockpit and the other would be a digital co-pilot. And so in that case, you would introduce essentially a certain amount of autonomy into the system. You need to have the perception and planning capabilities and also the human-machine system interactions to enable such concept. For many years, we worked on joint project with Sikorsky, and so we developed a lot of these technology jointly and transitioned them into full-size commercial military platforms. So what's shown here are some of the demonstrations that we did. So one of these is the DARPA Alias program, where we demonstrated autonomous motion planning capabilities, where a pilot could, or an untrained ground operator could operate a full-size commercial helicopter just from a tablet interface. And then there's on top, there's also the application where we have a joint mission between a Black Hawk helicopter and a autonomous ground vehicle performing a joint mission. So this just shows some of the range of applications we've worked on. And yeah, so it was basically how we got started with all of these autonomous planning, perception, capability development. So how we were doing all of this. So essentially at UTRC, we tend to develop some of the high-risk, low TRL level capabilities starting out within a simulation environment. So at this stage, we tend to work with a lot of external partners, university partners, other industry partners, and then leveraging some external funding to a certain extent. And then we would demonstrate some of these concept capabilities on low-cost, small UAV and UGV platforms in our in-house lab facilities. And once we validated some of these algorithms, we then would transition this into joint projects, working with with our business units. In that case, it was a Sikorsky aircraft. So we're starting out within their simulation environment where you would do hardware in the loop simulations to validate your algorithms on flight simulators and eventually integrate some of these capabilities onto full-size commercial products. So some of these optionally piloted vehicle demonstrators. So essentially, this is similar kind of workflow that we do with a lot of the applications across both the aerospace and commercial domains. So these are essentially some of the capabilities that we develop out of these early years in the autonomy program. So there's the autonomy architecture, which we try to keep as reusable, flexible, and scalable so that they can be applied across multiple application domains. And then there's the perception capabilities, which essentially takes the onboard sensor data and turning into models of the world around you. So some of the familiar things that you see here include SLAM, vision-based navigation, similar types of technology that you would see on autonomous cars, but within a helicopter domain. And then there's the human-machine system component, which is, of course, vital to these optionally pilot vehicles where you still have mixed human autonomous system interactions. And then there's the planning component where I mostly work in essentially how you take in the information provided by perception and making intelligent decisions about what the autonomous platform is going to do. And so, so what I should say is that Sikorsky. So that was somewhat so it was within UTC up until 2015. So up to that point, the autonomy program tend to focus a lot on the autonomous vehicle side of things. But afterwards, it's some transition into somewhat different application domains, but we keep some of the similar core capabilities that are shown here. So I'll talk about that a little bit later, essentially within the context of some of the human-robot collaboration work that we've been doing recently. And so, we have, just like I said, was the way we develop and transition these technologies. We validated all of the algorithms on our in-house lab facilities. So we still retain an outdoor lab. We used to do a lot of work with our autonomous vehicle platforms. And then we also is expanding some of the indoor test facilities where for some of the newer applications, we're looking at for indoor inspections, human-robot collaborations, that kind of thing. So we have a range of different platforms that we test our algorithms on. So there's outdoor ground vehicles and aerial vehicle platforms, and some of the indoor instantiations of that, and also some of the newer robotics manipulation platforms that we have. And so what are we working on currently? So the current instantiation of the robotics initiative is called the Intelligent Robotics Integrated Systems. So what we're interested here is essentially in collaborative autonomy between groups of humans and robots in applications such as manufacturing, service, inspection, and repair. So this is, as you can see, somewhat of a different application focus towards more broad-based business cases across the commercial and aerospace domains. So the idea is to add autonomy and intelligence to existing hardware platforms. So for example, you have these industrial robots that does largely automated tasks in isolated work cells. What we want to do is add some of the higher level perception, planning, and human-machine interaction technologies to enable them to work collaboratively with humans in a work cell. So that's the kind of application we're targeting. So this is just some of the broad application scenes we're looking at. So this includes inspection robots for buildings and aircraft types of applications. So to essentially, this is motivated by a lot of the business use cases across our commercial and aerospace business units, and then also advanced manufacturing, which again cuts across multiple application domains. Again, the idea here is to have collaborative work cells where you have both humans and robots working closely in proximity. So how do you develop the technology to enable that kind of concept? Okay, so this is essentially an overview of some of the broad capabilities we're looking at within this human-robot collaboration context. And so what you see is a lot of same themes carry over from the autonomous vehicle domain, but within slightly different application contexts. So we're still interested in planning. So how do you do high-level reasoning, multi-agent planning for human-robot systems? We're still interested in perception. How do you build up models of the world around you using vision lidar sensors? How do you do object recognition? How do you recognize human intent? And of course, we're still interested in system integration, so how you tie these systems together. So that's where the architecture component come in. But some of the newer areas include physical interaction. So this is the robotic manipulation aspect. How does the robotic platform interact with its world, the world around it? And also the system machine learning component, which has to do with how do humans and robots collaborate together, and how does the machine adapt to the actions of the human. So here we're interested in things such as robotic learning from demonstration, robotic learning from VR, and that kind of line of work. So what I'll do next is go over a set of research topics that we're currently actively working on. So the idea is not to go over too much technical detail, but more to present the overall problem statement that we're interested in, and also some of our technical achievements to date. And hopefully that will provide a platform to generate some discussions for areas for collaboration. Okay, so the first topic I'll talk about is essentially the hierarchical mission and path planning. So essentially the problem we're interested in here is essentially how do you go from an abstract specification for a task that you want an autonomous agent to do to concrete motions and actions that can be executed by the platform itself. So an example could be a cargo pickup and drop-off mission where you just want to go from a starting location, go to a pickup location to pick up your cargo and drop it at one of the drop-off locations and then return to start. And you would want to minimize the time of arrival, and then also subject to certain constraints such as avoiding certain no-go zones within the city. So as you can see, there's the complexity arise from multiple of these areas. So one is you need to optimize for multiple costs. So you have both minimizing your path lengths and also avoiding going into these no-go areas. So you need to sort of balance your time of arrival with some of these threat exposure constraints. And then you also had to handle multiple logical, spatial, and temporal constraints arising from these high-level specifications of how the sequence of you performing the tasks. And then you also have to deal with contingencies on multiple time and spatial scales, because a lot of times things don't always go according to plan. So if if there are other dynamics obstacles in your environment, or your mission specification changes on the fly, how do you handle these on the fly? So essentially, this means that you had to plan essentially your actions at multiple levels of temporal and spatial scale, so including both strategic decisions at the mission level and also the motion plans at the tactical level. So essentially, our approach to this is through a hierarchical planning type of framework. So this involves both making strategic decisions at the mission planning layer, where you sort of answer the questions of where do you want to go, right? So essentially, how do you perform this type of cargo pickup and drop-off mission, the type of tasks you need to perform, and a sequence that need to be performed. And then the path planning and trajectory planning layer, they answer the question of how these tasks gets performed, right? So essentially, how do you plan an obstacle-free trajectory, use your path planning algorithm, and then how do you handle the dynamics of the underlying vehicle platforms through trajectory planning. So this is one way to decompose the complexity of the problem, and also to handle of the different temporal and spatial scales that exist across a lot of these autonomous planning problems. So I just, in the next part, I'll just present some high-level overviews of some of the algorithms we've looked at for the different layers of these planning hierarchy. So at the highest level, what we look at is the strategic planning, essentially how essentially this answers the question of where do you want to go, right? So how do you generate the sequence of tasks that needs to be performed and what types of tasks you need to perform, right? So the way we handle that is through a constraint markup decision process. Essentially, you construct MDP approximate abstraction of the high-level planning problem. So the states could be as simple as different sectors of the city. The transitions essentially abstract the motions that are planned by the low-level path planner through each sectors of the city. And the advantage here is, of course, you can handle a rich class of mission specifications. You can specify the order in which systems are executed. And then also what types of tasks need to be executed. You can essentially optimize over that using this MDP abstraction. Just to provide some graphical illustration, essentially what we have is a high-level knowledge representation of the overall mission specification. And we have some automated algorithms, which turns this into an MDP abstraction of the overall mission that you want to perform. So essentially the sectors of the cities and the types of actions that can be executed by the path and trajectory planners. And then the high-level mission planning problem essentially turns into an optimization problem on the NTB process. So you can actually generate an optimal policy which then gets passed on to the next layer, which is a path planning layer. And then what we have is essentially a plan monitoring function to monitor if anything changes in the environment, and also if there are any pop-up obstacles that comes into your way, and how do you dynamically replan along the way. So that's somewhat of a separate topic. How do we handle that? Yeah, so going to the next level of the hierarchical planning, essentially that's where we have the obstacle avoidance. I think a lot of people are aware of some of these obstacle avoidance algorithms such as PRM, RRT, these sampling-based planners. But one of the extensions we looked at in this area is essentially how to consider multiple objectives within the path planning problem. So essentially, within this context, the problem you want to solve is to plan path from start to goal while minimizing a primary objective subject to a secondary constraint. So the secondary constraint can be multiple types of things. So it could be line of sight to a base station, fuel efficiency, or there's just part of the city that's a no-go zone that you want to avoid. So what this means is essentially the shortest path may not always be the best path to take. So how do you actually plan your obstacle-free path within that context? So the approach we looked at in this case is essentially an adaptation of essentially a Dijkstra's algorithm, but adapting it within a multi-objective context where you, instead of computing a shortest path from start to goal, you look at computing a family of paths which essentially forms a Pareto front that you can perform your trait analysis over. So in this example scenario, you have essentially what we refer to as a threat in the environment, but it's essentially could be a no-go area, no-fly zone, dynamic obstacle. You can think of it that way. And then what you want to do is minimize the path lengths while subject to a constraint. You want to be exposed to this threat as little as possible. So what you can see, essentially, we generate a family of these paths, and the color coding essentially is the secondary cost. So what you can see, the shortest path essentially gets you closest to this area that you want to avoid. So it says a high secondary cost. So if you want to minimize your exposure to that, you might want to take some of the longer paths around with some of these other trajectories within this family of paths. So essentially, this is our multi-objective path planning that we looked at. And then, so the last thing we have in this hierarchical planning is essentially a trajectory planning level. So this is looking at the problem of how do you generate dynamically feasible trajectories which follows the high-level path that's generated from the path planning layer. So essentially, this becomes a constrained optimal control problem where you need to take into account the underlying vehicle dynamics to generate a feasible trajectory. And essentially, your optimization variables are the actual controls of that you apply to the vehicle platform itself, and also the time instance where these trajectory points are reached. So essentially, it turns into a nonlinear constrained optimal control problem, and we developed an MPC framework to actually solve for these trajectories on board the vehicle. So just to tie some of these together, so this is one of the demonstrations we did where we have both the multi-objective path planning and the MPC trajectory planning all running on board a ground vehicle. Essentially, what you have is you have a ground vehicle is trying to reach from point A to point B while avoiding some threat along the way. And what you see is the multi-objective path planning generates a family of feasible paths through the environment, which avoids obstacles. But also, you can select a path along this Pareto front, which trades off the threat exposure. Essentially, if you want to be further from the threat, you would take a path which takes you further away from what this no-go area that you're trying to avoid. And also, let me play this video. So you'll see that there's also an MPC trajectory, which is generated to follow this high-level path so that it respects the dynamics of the vehicle, which we model as in this case, a Dubin's vehicle. So this is just showing it running within our ground control station visualization environment. But there's later in the video, it shows it actually executing this on our ground vehicle platform in one of our outdoor environments. Essentially, we have a ground vehicle that's outfitted with LiDAR sensors, which generates essentially a representation of the environment through SLAM. And then we use this to generate our path plans and also the trajectory plans, and then which gets executed on board the ground vehicle. So this is just showing the hierarchical planning executing on a full ground vehicle platform. All right, so with that, I'll go towards the collaborative autonomy. Essentially, within this area, what we're interested in are system architectures, which enables multiple autonomous agents to come together to perform collaborative perception and planning tasks within a distributed setting. So the idea is the system architecture here should be distributed, reusable, scalable, and agnostic to the type of vehicle platforms that we apply this to. So some of the work we've done in this area, of course, is a lot of the system architecture, for how do you design the autonomy software, and also how do you share information between the vehicles in a distributed setting. So one of the scenarios we looked at is a collaborative autonomy between aerial and ground vehicle, where you have the aerial vehicle acting as scout to essentially detect essentially the threats in the environment that are not visible to the ground vehicle. And this information is communicated to the ground vehicle, and then it performs the multi-objective path planning, which I was showing on the previous video. So essentially, instead of this simulated threat I was showing before, we actually have an actual aerial vehicle which is performing the target detection task. This is essentially just showing some of the autonomy architectures we've been thinking about for this collaborative context. So the idea is that it's a distributed architecture where we have multiple agents with knowledge sharing. So essentially what we want to do is share the perception information among multiple agents. Also design our software architecture such that there's minimal structural changes between different vehicle platforms. And that becomes this important when you consider the broad range of application domains we would like to apply autonomy to. So you would like some of these software structures to remain constant as you migrate across different application domains. So the collaborative aspect about this scenario that I was talking about, essentially, we had an aerial vehicle which acted as a scout, which detected this threat on the ground. So the thing to keep in mind, so a lot of this work is done within the time where Sikorsky was around. So some of them had somewhat of a military connotation. So essentially, the ground vehicle was is performing a convoy mission, and then so you have these threats which would be essentially detected by this aerial scout, and then so the ground vehicle would perform its convoy mission, essentially avoiding these threats on the ground. So what we have here is actually a vision-based detection and localization algorithm, which was running around on this aerial vehicle, doing the target detection in real time and communicating to the ground vehicle. And I don't know why it's not showing up. Oh. Huh. That's interesting. Okay, so maybe I'll just show this in this. Some technical difficulties, I guess. Okay. All right, so I'll just show the videos within this presentation mode. Essentially, what we have is, again, this outdoor test environment that we have. So we have an autonomous helicopter platform, which acted as the aerial scout, detecting a target on the ground, and this communicated to the ground vehicle platform, and then so it used that information to do its multi-objective planning, and you see that gets executed on the actual platform that we have. So it shows the collaborative autonomy aspects with joint perception and planning. So that was the idea there. Okay. So with that, I'll go on to some of the more recent work we've been doing in human-robot interactions. So within this area, the main idea is that instead of having fully autonomous systems, or fully manual systems, we're looking at some intermediate modes where we have both humans and autonomous agents working in close proximity and working in collaboration. So the motivation for that is there are certain application contexts where human operators might be preferred, especially if you look at a manufacturing context within aerospace domains, where there's still significant amount of intelligence, dexterity that are needed. So some of these tasks will probably continue to have a human component to it. But what you like to do is to bring additional levels of robotic automation, which improves the precision, repeatability, and also efficiency. So essentially, the idea is by combining human and robot in an integrated system, you could provide better productivity, flexibility, quality within a collaborative human-robot work cell. So some of the technologies that would need to be developed to enable that kind of applications would need to include, essentially the perception and planning and human-machine interaction technologies that I was talking about before to enable this safe and seamless collaboration. So some of the work we've been doing in this area, so this includes robotic learning from virtual demonstrations. So essentially the idea here is that, in a traditional industrial robot kind of application domain, what you have is either an expert programmer programming this function for industrial robots, or you have a human actually teaching the robot what to do. But a lot of this effort is fairly manual, and then it puts the human operator in danger when it's actually teaching the industrial robot. And also it lacks repeatability and adaptability. So every time the work environment slightly changes, you have to do this process all over again. So the idea is by leveraging the virtual reality environment to do some of this training, you remove some of the dangers which comes across when you have a human operator teaching the industrial robot. But also you introduce additional adaptability in the sense that if you include some of the machine learning components into this, once you've taught the robot manipulator to perform a task a few times, you can at least provide some limited generalization from some of these tasks to slight shifts in the work environment, the objects that you would like to manipulate. So this is just one of the demonstrations that we had for essentially a tool pickup task. So essentially the idea here, you want to learn the how do you pick up different types of objects that you would like to use for a manufacturing task. So in this case, it's just a screwdriver. So essentially it's learning the grasp points that you would like to use. So the idea is by doing this training phase within this virtual reality environment, you can teach it all kinds of different grasp configurations, and then use that to build up a model for how do you generate these grasp points when you see different tool poses and orientations in the environment, and use that on a robotic assistant type of application. So some of the other things we're working on, so there's some efforts going on in the Berkeley office looking into this distributed intelligent agents. Essentially, this is an instantiation of the high-level planning problem that I was talking about before. So how do you use multiple sensors and actuators or robotic agents within intelligent building to optimize for various types of objectives, right? So, one application we looked at is intelligent egress. How do you intelligently guide the human traffic flow when there's a fire in the building? How do you use these indoor building sensors to actually optimize for the comfort of the building occupant. And yeah, there's all kinds of applications within the intelligent building domain. And so some of the other areas we're looking at also includes intelligent manipulation and perception. So of course, when you have human-robot collaboration, we need to plan for the manipulation of the some of the mobile manipulator platforms. So that combines the mobile base and also the robotic manipulator that are on these platforms. And also, how do you actually recognize objects in the environment that you would like to interact with, and also the humans who are in this environment, so you can both do both for purposes for collision avoidance with the humans, and also for how these collaborative tasks, how do you do intent recognition and intelligent response to the human intention. So to just tie some of this together, I'll just show one of the demonstration we did essentially with this intelligent robotic assistant. So the idea here is that there's a set of tools that are spread out on a table environment, and the robotic assistant would use perception to identify the location and poses of the object, and then pick up the object and hand it over to a human operator. So there's both the planning aspect for the robotic manipulation, there's also the perception aspect of how you identify the tool poses, and also there's the human-machine system component where we have essentially a speech recognition interface which allows the operator to issue a command, for example, for pickup clamp, and then the perception system would essentially detect the location of the clamp on the tabletop, and then you have the robotic manipulation which goes and pick it up and hands over to the operator. So so this is a lot of this work. It's still in the early stages, so we're looking at the type of applications that you could use for this type of human-robot collaborations, whether within inspections or manufacturing context, and it's an ongoing area of development. So with that, so this is all of the topics that I was planning to talk about within the seminar. So thank you for all your attention, and feel free to ask any question that you might have. And also, well, I'll just leave it on this slide. So we're always, again, looking for people to join us. So certainly feel free to come up and talk to me afterwards if you're interested. All right, thanks a lot.
All right, we have time for a couple questions, if there are any.
Thank you for your talk first. And have you thought of using machine learning or artificial intelligence method for the mission planning, path planning, or such kind of problem?
Right. So I think so far what we looked at is essentially using machine learning within a perception context. But I think, yeah, there's certainly a use case for machine learning within the planning domain also, especially if you look at some of the more complicated task specifications. And I think in a way that also comes through in some of the learning from demonstration work that we're trying to do. So there's certain use cases where you can learn the trajectories from the human, and the autonomous system can mimic that. So there's only use cases for that. Yeah.
Any other questions? All right, let's think. Oh, wait.
So when you showed this example of the path planning and this Pareto curve,
Yeah, yeah.
I'm wondering how you decide where on the Pareto curve you want to choose.
Right. That's a good question. So far, we've been using essentially manual selection. So essentially, there will be a human operator who has a view of the entire Pareto fund, and he would select the desirable path along that Pareto fund. But yeah, you can certainly think about automated algorithms to actually select something along that Pareto fund. But yeah, so there are some challenges in that, how to best select a path that you would want, right?
All right, let's thank the speaker one more time.
All right, thank you.